Hi everyone, today's lesson is about linear motion and under a situation with a constant force. So there will be an acceleration produced. Now the scenario is that we have a constant acceleration. If the force is constant, then according to Newton's law, remember, the sum of the forces acting equals the mass multiplied by the acceleration. So if the force is constant, and by the force I mean the net force or the resulting force, then the acceleration is constant. Now let's describe the motion here. We've got the object. Here's a nice horizontal road, track. The origin is over here somewhere. The object does not have to begin at the origin. So we label the displacement. The letter S is used for displacement. More correctly, I suppose, it's used for the position of the object along this number line. Now, at the beginning, here's our person pushing on the thing. It starts with an initial velocity. So V0, the velocity when t equals 0. So over here, this is when the clock starts, t equals 0. So V, the original velocity, is usually designated by letter U. Sometimes it's just left as V0. And then after some amount of time t, so an elapsed time of t has occurred, some point in the future. Now clearly we've been accelerating, so our person pushing the box is moving quite a bit faster at some higher velocity v, sometimes called the final velocity, and the position is now s along the number line. Technically the displacement is the difference between these. The displacement is the s minus S0. Now, often we will begin the motion from the origin, so S0 equals nothing, and if S0 equals nothing, this is where we get the shorthand that displacement equals S. So, let's see how we go. We begin from constant acceleration. Now, we know that acceleration is the derivative dv dt. It's how quickly the velocity changes. So let's solve this. I would have dv equals a multiplied by dt, integrating both sides, v equals at plus a constant of integration. I'll evaluate that constant from my initial conditions here. So when t equals 0, v0 equaled letter u. So if I put V0 here, then I have A times 0 plus U, because that was the initial velocity. There we go. Well, plus the constant of integration, I suppose I should say. And therefore, clearly the constant of integration equals V0, sometimes referred to as U. This gives me my formula then, that V equals u plus a multiplied by t. And that's the first equation of motion. Now, how do we go about displacement? Well, we know that velocity is the rate at which the position changes. Separating out here, I'd have ds equals u plus a times t dt, integrating both sides, s equals ut plus a times t squared over 2 plus some new constant of integration. Once again, I'll evaluate from the initial conditions. The initial conditions were that when t equals 0, the position was S0 on the number line here. So if I replace this with S0, and I have u multiplied by 0 plus a by 0 squared over 2 plus c1, obviously c1 equals S0. So then I have s equals S0 plus ut plus 1/2 by at squared. Now that's probably not what you saw in physics class. Now this is not mandatory, but often S0 will be chosen to equal 0. In other words, often we will set the origin of our number line at the place where the moving object begins from. And if that's the case, then it just becomes S equals ut plus 1/2 at squared. And that's often what you'll find is used, because we get to choose where the reference point on our number line is. And for convenience, we'll often choose it to be the beginning of the motion. And if S0 did equal 0, if we put the origin here, then that part of the equation, that part there, just disappears. Now, it's sometimes handy. We've got two formulas. One gives us the velocity at some point in the future, if we know the starting speed, the acceleration, and the time elapsed. The next one gives us the position, the displacement, if you like, in the future, if we know the starting speed, the acceleration, and the elapsed time. Occasionally we get questions where we don't know the elapsed time. So let's eliminate time from these equations. Let's solve these simultaneously to eliminate t. Now from equation 1, we had that v equaled u plus a times t. v take u would equal a times t. v take u divided by a would equal t. Now let's sub into equation 2. Equation 2 said s equaled ut plus 1/2 by a by t squared. So t, we had v minus u over a. Now I'll write this as a over 2, and for t I had v minus u over a, which had to be squared. I'll put brackets on this too. So thinking of this as u over 1, this first one would be u times v minus u squared. The next one I would have a over 2 by, well, the a would be squared, and this would be v squared minus 2 times uv plus u squared. I can cancel that a there with one of the a's in the squared part. Then I have a denominator of 2 times a. I think I might multiply top and bottom of this by 2, so that I get a common denominator of 2a. S will equal a whole big bunch of stuff all over 2a. Now what would it be? Well, distributing here, I would have 2 uv minus 2 u squared. Then it would just be the bit left here, which is v squared minus 2 uv plus u squared. 2 uv minus 2 uv will disappear. I have, well, I might as well multiply by the 2a. I have 2 times a times s. Now there's a v squared, then I have u squared minus 2u squared, which is minus u squared. And this is sometimes written as v squared equals u squared plus 2 times a times s. And that is the third equation of motion. All of these apply only when we have a constant acceleration, because we started all of this back here with the idea that the integral of a constant a with respect to t was a times t. So I must stress again here that a is constant. If we had a variable force, none of this would be true. Now, fortunately, most of the time, we can find situations where the acceleration is constant. And so we can use these equations, the three equations here that I've got, in the highlighted boxes. But you should know the process of how to do this as well. Okay, thanks for watching.